All right, hello and welcome, guys, to part 2 of mathematical induction. This is one where we do the divisibility tests. All right, so we're just going to get straight into it. Actually, no, we're not. I'll just say, just before we begin with our first question, because it's mathematical induction, the whole concept is still the same. The idea is you need to show that if the theorem is true for one number, it'll also be true for the number after it. And then you combine that with testing it for the first value, and then you've got it, right? Ultimately, the proof is done by the mathematical induction. So although we're no longer testing that these two things are equal, we're just testing that there's this expression, and in this case, if you look at the first one, we're going to prove by using mathematical induction that 4 to the power of n take away 1 will always be divisible, right? That expression 4 to the n minus 1 will always give us an expression which is divisible by 3, as long as you're putting in a integer which is greater than or equal to 1, or in other words, all the positive whole numbers. So it doesn't matter if n is 1, 2, 3, 4, 1,000, 2,000,000 and 5. When you put that into this expression, it'll always give you a number that's divisible by 3. Before we go ahead and do the actual proof, let's actually check this out and see exactly how valid this particular one is. Let's say we let n equal 1, which is technically what our first step of the proof is going to be anyway. Check it out. 4 to the power of 1, take away 1, gives us 3. Hey, it's a number that's divisible by 3. And by the way, you guys know what I mean when I say divisible by 3. It's like if you were to divide that by 3, right, you get a whole number with no remainders, right? It's divisible by 3. Or in other words, the answer, right, could be written as 3 times some integer, right? So 3 is 3 lots of 1, it's divisible by 3. If we were to try n is equal to 2, right? So in this case, you got 4 to the power of 2, take away 1, was that 16 minus 1? You got 15, which, check it out, is 3 lots of 5. It's also divisible by 3. If you wanted to try n is equal to 3, right, here you go, 4 to the power of 3, take away 1. What actually is that? It's 64. Wait a sec. Here I am doing this. 54. No, that's a 2. Yeah, it is 64. So it's 64. You take away 1, you end up with 63, which is also divisible by 3, right? So we've tested the first 3 numbers. I guess you could keep on going on indefinitely. And at some point, you'd eventually get to the point where you're convinced it doesn't matter what value you put in. You're always, right, this expression here is always going to give us a value which is divisible by 3. But of course, we're not interested in like plugging in 1,000 different numbers to convince ourselves that it will probably always be true. We're just going to prove it straight away in the most efficient way possible. And that's what mathematical induction is. Well, that's the style of proof that we're going to use here. All right, so how does it work? Let's get into it. We're going to start off by testing the first value. Test n is equal to 1. So in this particular case, our theorem would be 4 to the power of 1 minus 1, which is equal to 3, which of course is divisible by 3. Divisible by 3. Therefore, you can say the theorem is true for n equals 1. All right, so that's the very first thing to do. Notice it's exactly the same as the previous maths induction proofs we were doing previously. Test the theorem for the first value that it supposedly works for, make sure it works for that value. Now we go on to the actual true induction part. We're going to assume it's true for a particular value, which we're going to call k, and then we're going to then test and make sure that it will also work. If it's true for that k value, we will show that it will also definitely be true for the value after k. So how do we do that induction step? Just like we did previously, we start off with our assumption. We're going to assume theorem is true for n equals k, i.e. 4 to the k take away 1 will be divisible by 3. In other words, divisible by 3, it'll be a number that's 3 times like some whole number, which we're going to call m. Why? Because, well, that's the letter all the textbooks use, let's be perfectly honest. Where what actually is m? Where m is an integer. But what we're going to do is, like, we're going to start using some abbreviations here, where m belongs to the integers. Right? That weird sort of a C with a horizontal line through the middle, that means in mathematics belongs to. And this like weird Z, capital Z type thing, that's the symbol for the integer numbers, which is all the whole numbers. Okay, so we're assuming the theorem is true for this value k. That means if you have 4 to the power of k, take away 1, it's going to give us a number which is like, well, divisible by 3. In other words, 3 times some whole number. All right, so there's our assumption. You guys probably know what's next. Now we're going to consider when n is equal to k plus 1, right? The next value along, i.e. 4 to the k plus 1 take away 1 will also be divisible. I'm abbreviating divisible here. Is divisible by 3. Okay, so let's start off with what we have. So if n is equal to k plus 1, we're going to have 4 to the k plus 1 take away 1. We need to show that provided our assumption was true, this here will also be divisible by 3. Right, so we want to get it to a point where we can like factor out a 3, and that would show that it is divisible by 3. All right, so how do we do it? Well, we need to use the assumption. Here we go, 4 to the k minus 1. Well, in this case, I'm just going to rearrange it so we can get 4 to the k. That's the thing that we're going to sub in here, 4 to the k. Because we can't get 4 to the k minus 1, but we can certainly, here, we can isolate the 4 to the k. So remember, 4 to the k plus 1 would actually be 4 to the k times 4 to the 1, right? This is index law number 1. Remember when multiplying algebraic terms that have powers, the powers add together? So if you had 4 to the k times 4 to the power of 1, that would actually give you 4 to the k plus 1. So I've actually just done here index law number 1, but in reverse, if that makes sense. And then I'm just going to throw that 4 out the front. Okay, now we've got this 4 to the k isolated. I'm now going to make the substitution, right? For 4 to the k, it was 3m plus 1. So 4 to the k is 3m plus 1. Whenever you make a substitute, whenever you're using the assumption for n equals k, you need to state that. You know, you got to let the marker know what you've done. So we got this line by using assumption for n equals k. And then from here, what do we get? 12m plus 4, take away 1. 12m plus 3, check it out. We can now factorize out that 3. Right? And so now we've actually got, since 4m plus 1, like m is an integer, a whole number. So 4 times a whole number will also be a whole number, plus 1. Right, this 4m plus 1 is going to be a whole number. 3 times a whole number is definitely going to be also divisible by 3. Why? Because 3 is a factor. So once we get to this point here, we can actually say, right, which is divisible by 3 since, well, 3 is a factor, but more importantly, I guess, 4m plus 1 is an integer, right? It belongs to the integers. It's a whole number. So the fact that we've got that 3 there makes the whole thing work. So that's actually all the mathematics required for the proof. So what we've done is we've shown that the theorem works for the value 1, right? That's that step there. We tested the value 1. Hey, it worked. It gave us a number divisible by 3. And then what we've done is we then went ahead and just assumed that the theorem works for this random value k. And then through here, we've shown that if it worked for the value k, it'll actually also work, that needed to be extended down, it'll also work for the next value along. And so that's the mathematical induction proof. All we need to do is just do our final conclusionary statement and it's done. So therefore, the theorem is true for n equals k plus 1 if true for n equals k, since theorem is true for n equals 1, theorem will be true for, check out how it actually was stated in the actual question, for all integers n greater than or equal to 1. Which just means it's now going to be true for all the positive values, just following on from what we've shown. So since theorem is true for n equals 1, theorem is true for all integers n greater than or equal to 1 by mathematical induction. And that there is how you use math induction to prove a divisibility theorem. Okay, so now we've shown it does not matter. You can plug in any whole number that is equal to 1 or larger than into this right here, and you will always get a value which is divisible by 3. Kind of cool. And something that, I certainly wouldn't expect just based on the surface of it. And we saw you plug in the first couple values, it works. Surely there's a number where it doesn't, but we've actually shown that that's not the case. You'll always get a number divisible by 3 if you plug it into 4 to the n minus 1. So kind of cool. All right, so the next question we're going to do is we're going to prove by mathematical induction that's, okay, so one that's slightly different. So we're going to prove that 3 to the n plus 7 to the n is divisible by 10. And it is for all positive odd integers. There's shortcuts for all positive odd, there's shortcuts for all this sort of stuff. You don't need to know it, and you'll never see it in a HSC question, but often you see these sorts of situations. If we go back to the first one, for all integers n greater than or equal to 1, the way you could state that, and this is nothing you need to know, this is just out of curiosity, but that there, upside down capital A, that's a symbol for all. So you could say for all n belonging to the integers, and then that means such that n is greater than or equal to 1. That there is a shorthand way in mathematics, and for anyone that does do some mathematics at the university level, you'll probably actually learn this sort of notation. This means for all values of n, right? No matter what, n is some value that belongs to the integers. So the first part tells us, n is an integer value such that n is greater than or equal to 1. So all the integers starting from 1 and going up. It just sort of saves you having to write words because, hey, words are the worst. Let's be honest. All right, anyway, on to our second example. We want to prove that this expression here, so 3 to the n plus 7 to the n, if you plug in in this case, it's not any positive integer, it's any positive odd integer, you'll get a number that's divisible by 10. So that's kind of cool. I actually think the even ones give you an answer that's divisible by maybe 5. Anyway, we don't need to go into that. Let's just do the question. Let's keep it real simple. How do we do it? Exactly the same way we did the first one, right? Maths induction is easy because it's predictable. You follow the same process each time. All right, test the first value possible that it supposedly works for. So the very first positive odd integer would be the value 1. All right, so let's test it. Does this give us, here we go, we get 10, hey, check it out, which is divisible by 10, right? Because obviously 10 is equal to, 10 times 1. All right, so therefore, the theorem is true for n equals 1. Okay, next step. Now we get into the induction part. We're going to assume that the theorem is true for n equals k, i.e. 3 to the k plus 7 to the k will be divisible by 10. In other words, it'll be some number that's 10 times, some integer, where m belongs to the integers. And of course, that could be written in words, but, you are allowed to use this notation. There's no doubt about it. Okay, so we've done our assumption. Now you know the next step. Now consider when n is equal to k. Okay, what's our next value along? Check it out. This theorem, we're only testing that it works for the odd integers. So since k, we're assuming it works for k. We're assuming k is odd. If I do k plus 1 here like we normally do, if k's odd, what's k plus 1 going to be? It's going to be an even number. We are not testing to see if this works for even numbers. The fact that it says odd numbers probably tells us that this theorem doesn't work for the evens. It only works for the odds. So we're not testing k plus 1. We're testing the next value along. And since we're only testing odds, right, we need to test the value k plus 2. A little sneaky there, but hopefully not that difficult, and hopefully it makes sense to you. So we need to consider this situation, i.e. we need to show that 3 to the k plus 2 plus 7, I don't know why I wrote a 4, plus 7 to the k plus 2 is divisible by 10. All right, so let's check it out. What do we have? 3 to the k plus 2 plus 7 to the k plus 2. Okay, so what is this equal to? So again, just using index law number 1, but in reverse. 3 to the k plus 2 is technically going to be a 3 to the k times 3 to the 2, right? And this would be a 7 to the k times 7 to the 2. So in other words, you end up with 9 times 3 to the k, and this would be a 49 times 7 to the k. I've gotten to the end of the page. Going to yes. There we go, pretending I'm Tony Stark again. Yeah, wow, using technology, so cool. Okay, all right, so let's continue on with where we're going. So in this particular case, we're kind of, there's nothing, like there's no way for us just to factorize out a 10. And by the way, if we could do that, we wouldn't even need to use mathematical induction, let's be honest. We need to use our assumption. We haven't used that yet. Let's go back to where our assumption is. Here it is. So there's no way we can get like just a perfect 3 to the k plus 7 to the k from this, right? Because there's these extra numbers attached. So, you know, maybe we'll just rearrange and just get one of them. To be perfectly honest, it won't really make a difference which one we get, but we do need to sub in our assumption at some point, and now's the time to do it. So I'm going to throw in, 3 to the k. So obviously, if 3 to the k plus 7 to the k is equal to 10m, 3 to the k would of course be equal to 10m minus 7 to the k. That's going to be our substitution. So using our assumption, 10m minus 7 to the k. This is 49 times 7 to the k. Okay, so what do we get? We get 90m minus 9 lots of 7 to the k plus 49 times 7 to the k. Notice we have these 7 to the k terms. They're like terms. 90m is sort of stuck by himself. But we've got here, check it out, 49 lots of 7 to the k. Take away 9 lots of 7 to the k. So we've got 49 of these things. We take away 9 of them. We're going to be left with 40 lots of 7 to the k. And check it out. Now we can factorize out that 10. Why do we want to factorize out a 10? Because we're trying to show that it's divisible by 10, right? That's the theorem, that it's divisible by 10. So when we were going through this step of considering n equals k plus 2, and we started right here, let's be perfectly honest, our whole way through this working out, our main goal, our only goal really, is to show that it's divisible by 10. We need to be able to factorize out a 10. We've done it right here, down the bottom, which is divisible by 10, because hey, 10's a factor, and you know, this other number here, this 9m plus 4 lots of 7 to the k, right, belongs to the integers. It's also a whole number. If you had 10 as a factor, but the other number attached to it was not a whole number, like for example a decimal, check it out. That does not give you a number that's divisible by 10. The only reason having 10 as a factor out the front here makes the thing divisible by 10 is if the other number also happened to be, you know, an integer of some description. You know, it doesn't matter what the integer is, but the fact that the other number is an integer would then of course give you things that are are numbers that are divisible by 10. So hopefully that makes sense why we need to state this. Just purely having a 10 out the front does not help you. Not without having evidence that the rest of it would actually also be an integer. And how do we know it's an integer? Why? Because at the risk of having too many errors, let me get rid of some of them. M is an integer, right? Go back to our assumption. M is an integer. So we know that M's an integer. So 9 times, you know, some random integer is going to be a whole number. K is also an integer. It's an odd integer, but you know, if you have 4 times 7 to, you know, some number, it doesn't matter what it is. Well, it's, for this question, it's always odd. That will also give you a whole number. So you end up with like these 2 whole numbers that are adding together. Of course, the whole thing is still going to be a whole number. And that's sort of why it works. I don't know if that makes sense or not. Hopefully I didn't confuse you there. But that's why I'm stating this this part over here on the right hand side that I am. All right, anyway, that's actually the proof done. So therefore we showed that, you know, n to the k, n equals k plus 2 is also divisible by 10. So therefore theorem is true for n equals k plus 2 if true for n equals k. Since I apologize for the messiness of the writing, since theorem is true for n equals 1, therefore theorem is true for all. And again, you know, we would have that symbol we wanted, you know, for all if we wanted to. But therefore theorem is true for all odd positive integers. I think that's what it said in the question. By mathematical induction. By the way, if you see the textbook, they might, you know, write this, or if you see like, you know, maybe you've got a friend or a tutor, they're showing you this sort of stuff, they may actually write this final conclusionary statement slightly different. You know, they might have, you know, some different words they use. That's totally fine. Obviously, you just can't completely ignore it. You do have to write something there to express what's gone on. But don't think the way I'm writing it is the only way to write it. You know, there's lots of different ways. As long as there's something there that shows what's happened, you should be pretty good. Now, to finish off this lesson, I'm just going to pick out like one more question from the exercise that you've got coming up, which is maybe a little bit different. I'll be honest, I say a little bit different, but they're all kind of done the same way. They're a stack load of fun. Question 13, question 12, the very last, like this, admittedly I've done a lot of these. They are a stack load of fun. I won't lie. I don't want to ruin by just doing all of them for you. I'll do one more. I'll show you question 12 because it's a little bit different to the first two that we've just done here. And in this case, we want to prove that 6 to the n plus 10n minus 6 is divisible by 5 for all positive integers such that, you know, n is greater than or equal to 1. Sorry, I've abbreviated the. You'll see the question in its full entirety with words when you go to the exercise, which is exercise 9.2, right? Obviously. All right, so how do we go ahead and do this proof? Let's quickly just go ahead and do it. Sorry, I'm rushing a little bit because I've got a 2-year-old that's just starting to make noise. I think he's starting to wake up. So this theorem here supposedly works for all positive integer values. Let's test the very first one. Will this thing always give us a number divisible by 5, right? It seems unlikely. You got the 6 to the power of n plus 10n, take away 6. Will you always get a number that's divisible by 5? Of course, you can start plugging in a couple different values for n to see that it actually does work, and you'd be like, wow, it actually really does. I wouldn't have thought so. Let's go ahead and prove it. Let's test it for the first value. So in other words, you end up with 6 to the 1 plus 10 lots of 1, take away 6. This ends up just giving you the value 10, let's be perfectly honest. Which, of course, not that you need to write it, you could just state it, but hey, I'll break it up, right? That 10 is 5 times 2, which, of course, is divisible by 5. All right, first step is done. Next step, assume theorem is true for n equals k. So in this particular case, i.e. what's that going to be? It's going to be that 6 to the k plus 10k, take away 6, will be divisible by 5. So in other words, it'll be a number that's like 5 times an integer, where m belongs to the integers. Specifically the positive integers, you know, but it doesn't really matter. All right, so that's our assumption done. Now we're going to go on and consider the case when n is equal to, this theorem works for all positive integers, so the next value to consider would be k plus 1, right? We didn't have to like skip a number to keep it odd or to keep it even. You know, you might get ones like that. We could just go on to the very next value. Okay, let's see if this thing actually works for n equals k plus 1. I.e. 6 to the k plus 1 plus 10 lots of k plus 1, take away 6, is divisible by 5. This is what we're trying to show, right? We're trying to get this. We're trying to get to a point where we can factorize out a 5. So let's go ahead. Again, I'm breaking up this k plus 1 the same way we have been in the other previous questions. This would be like 10k plus 10 take away 6, right? Most people would skip this step and straight away they would have looked ahead and seen that you can write that as 4. Okay, we get to this step and we sort of hit a roadblock. There's no other like terms or anything like that we can do. This is the point where when you get to this step, you go to your assumption and we need to bring in our assumption. Let me see if I can get this to copy. Paste. Okay, so what is our assumption? So we've got a 6 to the k, we've got a 10k. Let's bring one of them in. I'm going to sub out probably the trickiest part to deal with. I don't want 6 to, you know, it wouldn't actually matter. You could like rearrange this to have 10k is equal to, and it will still work great. I won't lie. But I actually don't want to deal with 6 to the k. I want to sub it out. So I'm going to rearrange this thing so I can get what 6 to the k is equal to, and this is the substitution I'm going to make. So 6 to the k is that. Let's see if I can remember it. Okay, so it was something I've already forgotten it. I actually made it perfect. 5 to the m, take away 10k plus 6. 5m, take away 10k plus 6. Anyway. Alright, so you make your subs... Oh, and we should stay... This was... How do we get this line? We used our assumption for n equals k. Alright, so we end up with 30m. That's divisible by 5. So that's kind of cool, right? Remember, we're trying to show it's divisible by 5. We want to get to a point where we can factorize out of 5. This is a 60k, also divisible by 5. This is the 36. That seems bad. Until you consider we have the plus 4 at the end there. Anyway, collecting your like terms. And here we go. Bang, bang. Actually, end up being divisible by 10. But anyway, we weren't showing that. We're just trying to show that this thing is divisible by 5. So get to a point where you can factorize out the 5. And is this other thing going to be a whole number? Noting that m is a whole number and k is a whole number, and of course it is. So we can say which is, so this number, 5 outside of all of that, it is divisible by 5 because since, due to, I'll write since, I think that's what I've been writing, since 6m minus 10k plus 4, is an integer value. It's the only reason it works, as discussed previously. And that is the question done. And then you go into conclusionary statement, which I'll just say, hey, therefore, theorem true by math induction. Don't, make sure you write out the full one, but I actually do need to wrap up here because of issues stated earlier. Mind you, at university level, I actually think that's all our professors, when we were doing maths induction, they knew what maths induction was. Everyone else in the course knew what maths induction was. The only people that might potentially be looking at our solution already understood the concept of math induction. You didn't need to spell it out in your conclusionary statement. Once you'd shown it mathematically, you could just state it there at the end, which is kind of cool. But anyway, that's not for you guys yet. Hopefully this made sense. Best of luck with everything. Please let me know if you have any questions, and I'll help however I can. There are some really fun questions in this exercise. So, if you skip it, you're doing yourself a massive disservice. Not to mention just all the fun and the lols that you miss out on. Best of luck with it, and I'll see you in the next one. All right, thanks, bye.